Well, hello everyone. Thank you for coming to our talk about Suricata. It's great to be back here after 3 years. Back in 2008, when we had just received our funding, Matt Youngman and I were here to announce our plans and solicit for ideas. And so 3 years later, and it seemed like a good moment to come back and tell you about what we're doing now and where we are. Those of you that attended Aaron Finnan's talk yesterday, they might have heard a pretty pessimistic story about how IDS is doing and about especially its detection accuracy. I'm not quite as pessimistic, although there are definitely some issues, but there has been a lot of progress. This talk is from Eric LeBlanc here and myself, Victor Julian. Let me quickly introduce Eric. Eric is a security and open source professional since the end of the 20th century. He has created and has been the lead of the NU firewall, an enterprise, a project aimed at creating an identity-based enterprise firewall. Eric is a long-term contributor of NetFilter, the packet filtering framework for Linux. And among other things, he has made major contributions to ulog2, the user space logging daemon. He's a frequent speaker in French, free software and security conferences, and also writes articles in the specialized press like Linux Magazine France. He has, for example, been the main author of the special NetFilter issue. He was also the co-founder of INL Edenwald company, where he was a CTO to build enterprise-grade network appliances based on NU firewall. Eric is now a freelance security consultant in free and security software, and he works currently for OASF among other things. And for OASF, he is the maintainer of the packet acquisition system and our inline and IPS support. A little bit about myself. I'm the lead developer of Suricata. Some people may know my other project, which is Vuurmuur. It's a firewall front end for IP tables, but most people pronounce it as Vuurmuur, which is mostly the English-speaking people. I've worked with Snort Inline for years as a developer, and also as a contractor, I've done lots of work on Snort. In late 2007, about 4 years ago, I started working on a little multi-threaded packet forwarding program, and it got a little out of control, and here we are. So the next 40 to 45 minutes we'll be talking about Suricata. Well, I will tell you quickly about what Suricata is, who builds it, why we build it, how it works, what makes it great. I'll be highlighting some major features. After that, Eric will be showing some recent advances in Suricata in how it deals with SSL and TLS traffic. There's a lot of things going on in this area, especially I'm from the Netherlands, and as a Dutch guy, I don't like being reminded of DigiNotar, the certificate authority that was hacked, and Eric will show us some things that we can do there. SSL is definitely a topic that's hard for an IDS in general, but we can do some interesting things there. So after Eric is done with that, I will be returning to the stage and tell you about file extraction, one of the new features we're working on in Suricata. So what is Suricata? Suricata is a network intrusion detection and prevention system, or really engine. It's really an engine, but people are so used to saying system that we kind of just keep using that as well. But really, Suricata on its own is only of limited use. You're supposed to use it in a much larger ecosystem of tools to do complete detection in your network. Suricata is open source with most of its code GPL v2 and some parts under a BSD license. Suricata works by looking at network traffic. It inspects each packet. It's against known bad, which means we use signatures heavily. In addition to this, we detect all kinds of anomalies during parsing and decoding of the traffic, and so we can detect that as well. Suricata uses the snort signature language, so existing rules are generally supported, but I'll go into more details later. Suricata is built by us here, but also by a whole lot of other people. The development is organized around the Open Information Security Foundation, which is a US-based nonprofit, and it's funded by the US Department of Homeland Security, also known as DHS. They've pretty much stalled us with the funding to do something good with it, with no specific deliverables, so Suricata is what we're doing. Using this funding, we've been able to pay developers to work on it, and also we have spent some of our funding on other development, like we've developed, or we have asked Ivan Ristich, who you might know from Mod Security, to write a specific security-aware HTTP parsing library. Another example of using this funding to support other projects is we did some funding of the Barnyard 2 tool, which include for work to include the SnortSam tool, which SnortSam is a tool to send block commands to your firewall based on snort rules or Suricata rules. So we have funding, but for the longer term, we're looking at vendors to support the project. And we formed a consortium where companies that have an interest or a stake in Suricata can support us. And usually they support it by cash, or they support it using or giving us access to some of their developers to help us build things. And this is a slide with some of the companies that are helping us currently. So how does Suricata work as an IDS? Well, the first thing is we process packets. So we need to be able to see packets. So a network IDS you usually place in the network, and in a switch network, it's always a challenge to get packets to the IDS. So you usually you control configure your switches to use some kind of span port and send all the traffic to your IDS. So once you've done that, the IDS sees the packet and it needs to try to understand them. So for this, it starts decoding them. It takes the packet apart. It parses the IP header or Ethernet headers, IP headers, TCP headers. And at some point, when this is all done, Suricata will know all about the packet. Some packets are fragmented, like Aaron also showed in his talk yesterday, but we have a defragmentation engine, so that's taken care of. For TCP packets, after the decoding stage, we will start reconstructing TCP sessions, reassembling the data layer, and find all kinds of anomalies like retransmissions with different data and all kinds of other things. So at the end of this stage, we have a reassembled stream that can be inspected. But we do more with reassembled stream. We go to, we have an advanced HTTP parser and a few other parsers like the TLS parser Eric will be speaking about. And what we do based on the reassembled data is reconstruct the full HTTP session. this is done in a stateful way, so every new data just updates the state, and we keep a state of the entire HTTP session. So if that's all complete, then we're ready to do detection. And in the detection stage, all the packet, the stream, and the state are inspected against the rules. And the rules here are the signatures, as you may know them from Snort, but also all the anomalies we detect during parsing and decoding are exposed to the rule language, so you can have rules that do specific matching of on these anomalies. So in the detection, so if the detection finds alerts or find rules that match, alerts go to the output stage, which is the final stage. Here an alert is processed by various output plugins. The most simple one is a Snort-like fast log, but we also support Prelude and Unified 2 to support all kinds of other tools that are available. So we can also work as an IPS. The big difference there is that instead of just detection, we can do prevention. The IPS mode is supposed to be inline, so the IPS gets in between the various hosts. And in general, it will pretty much work the same way internally as the IDS. However, we do some other things like normalization of especially HTTP streams. There is a lot of anomalies and evasion possibilities, like Aaron discussed yesterday, which are we can remove from the stream. So then we really alter the packets on the network. Of course, the rules can be set to drop packets and streams based on the matches in the rules. So IDS has a lot of limitations. It has even been declared dead by Gartner, the researchers, but we feel it's far from dead. There are some issues like Aaron discussed yesterday. The first problem we have with IDS is that it's fairly easy to overwhelm it. Usually an IDS is sitting on a span port in a switch, and usually, or in many occasions, this span port does not have the full capacity to get all the packets on a fully loaded switch to the IDS. So there's the first problem of packet loss. Another reason IDS is fairly easy to overwhelm is because IDS operations are quite CPU intensive and expensive. An IDS has to keep an internal representation of about dozens or hundreds or even thousands of hosts and their network activity. So if you, for example, take a 10 gigabit network, you could be talking about 15 million packets a second that need to be compared and parsed, and you would inspect them, for example, against 10,000 or 15,000 rules. So it's quite easy to see that just these numbers will lead you to very heavy hardware requirements, and not everyone has it. So packet loss is always a problem. A different problem is what we call impedance mismatch. This issue is also got some attention under the name of AETs, or advanced evasion techniques. So what it means is, and it's in part the same thing that Aaron was discussing yesterday, is that there is ambiguities in the network traffic and in the way OSs and programs are handling these ambiguities. And the IDS has to make a choice, like what way to interpret traffic. So for example, Aaron discussed differences between Apache and IIS web servers, or even Apache on Windows and Apache on Unix. But differences like this exist on every layer we're looking at, and usually get worse the higher you get. And I have an example here. This is a table I took from Ryan Barnett's Technical Web Application Security blog, and it shows what the IDS, IPS, or WAF has to deal with. Ryan investigated a simple question: how does the web application respond if it receives multiple parameters, HTTP parameters with the same name but different values? And as you can see, the result is quite dissatisfying. This is just one list of frameworks, web application frameworks, and many have all kinds of different ways of interpreting this. And this is what we're seeing all over the place. It's just quite a mess. False positives are an obvious problem in IDS. We've had problems with, in part due to poor rules, or the engines not being able to expose enough specific enough buffers. An example of a buffer here would be a URI or a HTTP method or something like that. So if you try to match on something that's not specifically exposed by the IDS engine, you will have to be creative in the rules, and often this leads to false positives. False negatives are obviously an even bigger problem. They can, again, come from bad rules. They can come from engine bugs that do poor or normalization, missing decoding. And of course, packet loss is a major issue for false negatives, and other resource starvation issues where you would overwhelm the IDS so it cannot inspect everything is a big issue. So the last thing I want to mention about the limitations is encryption. Obviously, encryption is hard for an IDS because usually you cannot decrypt the packets or the sessions. And with HTTPS and SSH traffic, for example, that's a big problem. There are some SSL decryptor options, but Suricata at least doesn't support that directly. So what does Suricata do to deal with this, or also known as major features? Well, the first thing is that Suricata will really help you to get the most out of your hardware. So we are using multi-threading, we're supporting out-of-the-box hardware capture cards, and we're experimenting with GPU acceleration. The second thing is Suricata uses automatic protocol detection for higher level protocols, such as HTTPS, and I'll go more into these after this slide. We support large IP blacklists. There's a lot of information out there on the internet on IP addresses, and the IDS is an interesting place to use it. And we have very thorough HTTP inspection and logging, and HTTP is obviously one of the more important protocols. So multi-threading. One of the core ideas to Suricata was to make it multi-threaded. The reason is probably pretty obvious. Even your smartphone nowadays usually has a dual core. Your next tablet might have a quad core. A server with 2 quad core boxes and hyperthreading, which leads to 16 logical CPUs, are already quite cheap. Intel has a 10-core Xeon with hyperthreading enabled. It's 20 threads. AMD just announced a 16-core Opteron, and Tylera, which not everyone might know, has CPUs with 64 and 100 cores. So using that or trying to really exploit those hardware features is high on our list. So Suricata has a highly modular threading design, which allows us to experiment a lot with all kinds of threading configurations, from a completely single-threaded model where we just run one single thread to many hundreds of threads. There is a paper in which people tested Suricata, and they somehow managed to get their hands on a box with 576 cores in it, and it worked with Suricata. It just used them all. Sadly, they didn't really investigate the scaling. They just compared it to Snort, which was an unfair comparison because they just ran one Snort and one core. But it was cool just to see that it actually worked. So far, From our experiments, it appears that flow-based load balancing between threads is performing the best. And we can do this with a single packet input, such as libpcap, which then distributes it over all the other threads for the processing, or we can use, for example, pfring, a packet acquisition method, can expose multiple readers, so we can have load balancing in the kernel instead of in user space. The next version, we're expecting to have the same kind of support for NDACE network cards and NAPATEC cards. Talking about capture cards, NDACE and NAPATEC are the two where NDACE is already working. NAPATEC is what we're working on currently to get integrated. These are usually very expensive cards. I think they start at something like 10 to 20,000 euros or dollars, I'm not sure. But they are really required if you want high-speed packet capture. And in general, what they do is have huge buffers to minimize packet loss and all kinds of things. So not everyone has the deep pockets for those cards, so pfring is a poor man's equivalent. It works on all kinds of hardware, but has special support for certain types of network cards. GPU acceleration. Like I mentioned, we're experimenting with this, and we're currently using the CUDA framework for it. The potential of the GPU is very appealing. It's very, very fast if you manage to get it operated right. But it turns out to be a lot harder than we anticipated and hoped. So we have an implementation and it does work. However, it is slower than our CPU implementation, which kind of defeats its purpose. So we're actually in touch with NVIDIA to try and improve things. And OpenCL is one of the things we want to be looking at. OpenCL is the platform-independent CUDA-like API. It is supported by AMD, for example, as well with their ATI cards. And Intel even has some support for it. And just yesterday, Intel announced some, still a little bit vague, but they announced some GPU-like hardware that's supposed to be like the GPU, the CUDA. It's supposed to be working like with OpenCL or CUDA, I think, and it has like 50 cores or more, but it's still a little bit vague. But there's a lot of movement in this area where you would offload certain types of operations to specific hardware, but programming is quite hard. So one of the features I mentioned was high-level protocol detection. And this has been especially helpful in detecting malware. The idea is that we have special code that allows us to detect the protocol on independent of ports. And for example, previously you would have a rule in Snort that would probably look something like this. You would, if you would be looking at HTTP traffic. So HTTP ports, the variable here that controls on which port we would be looking, is usually set to something like 80, 81, and a few others. But if you would be out of luck if the malware or whatever you're matching against is on a different port. So what we have extended the language to be able to say alert on HTTP, which means we'll be relying on our protocol detection, and then the detection can be on any port. This has actually helped, especially malware detection, enormously, because a lot of malware uses HTTP traffic for command and control, and they often use off ports, so the non-standard ports. and we're seeing much better detection rates because of this. High-speed IP matching is one of the things I mentioned. If you know the Emerging Threats Project, they have enormous lists of known bad IP addresses, compromised, suspected Russian business network, all kinds of things. And previously, you had to choose between a few of those rule sets to be really using them in a performance-efficient way. So we have created a special module in our code to just be able to load them all and get alerted or drop even the hosts if one of your hosts is contacting such a blacklisted host.
Is this also supported by the hardware accelerator cards? Or?
No, this is all in software, yes. So like I already mentioned, our HTTP parsing is done with libhttp, the library written by Ivan Ristic, who is the author of Mod Security and currently working on IronB, another WAF and a web application firewall. So because HTTP is so important, we figured we get help from someone that really knows what he's doing in HTTP. So this is the library he wrote for us. It constructs a full state of the HTTP session that we constantly update. It can track all transactions, and it allows us to do, for example, file extraction, but I'll get into that later. libhttp is available outside of Suricata. It's a GPL licensed library in the older versions, and newer versions are even Apache licensed, so it's even more liberal to integrate into any tool you want. And one of the things we do with it is a simple request logger that, for example, should be an example here. So this is on a single line normally. It's a simple log that's kind of resembling the information an Apache access log, for example, has, and it just shows that for everything. It's quite useful to see what's going on in your network. Eric's next.
Hello, I'm here to present you the TLS support in Suricata. TLS, as mentioned by Victor, is an application layer which is supported by Suricata. And an application layer has two interesting features, which is independent of port, because we have automatic detection, it uses pattern matching to find the protocol, and thus we do not rely on port. And it uses a dedicated keyword that we can use to match some specific part of the packet. For example, in HTTP, we've got a keywords to match the URI or to match the cookies. And this is the same for TLS support, which has also some keywords. And these keywords can be used in signatures. The Suricata application layer is composed of multiple protocols, as you can see on the slide. What is the TLS support in Suricata? This is a TLS on-check parser. We did not decrypt the traffic. We just analyze the on-check by getting every packet and checking every message and decoding every message to be able to know which certificates are exchanged, which parameters, algorithms are used to do an TLS negotiation. We decide to do our own security-oriented parser for this TLS on-check. The point was not to use OpenSSL directly. OpenSSL is very big, and we want to be able to audit the code and to test it, to be able to hack it, and to be able to, for example, to have some event related to anomaly detection. And for that, we need to have our own code. Thus, the code has been developed from scratch by Pierre Chifflier, which is working from ANSSI, which is the French Network and Security Agency. And he had developed it with security in mind. That he has made some audit with some other colleague. I made some audit too, and he has first the code to be able to validate that he will resist to attack or things like that. But what can we do with this TLS support? First thing is the same thing that Victor showed you on HTTP. You can just say alert on TLS instead of saying alert on TCP, which will give you some very advantages because you're not dependent anymore of the IP parameters. You don't specify any port, any the TCP port, for example, and that's why you just can have more flow study by the parser, and thus you can detect anomaly. For example, if you have a control and command channel which is done on some unusual port, and using TLS, you can detect it, and for example, detect some generic certificate that are used that you want to block. And one of the advantages of using this application layer is that you limit the match to the correct protocol. You don't try to do some pattern matching or some binary stream. If it's not TLS, you could have a match, for example, if you have a match on something like 5A, like we have in the previous talk about IDS version, you will easily match, but if you check this, for example, on some TLS protocol, having 5A will be very strange. And by doing this, we just run the signatures on the good protocol, which means that you will not try to analyze the traffic on on all packets, but just on packet with the correct protocol. Doing this, you limit the number of packets analyzed with signatures, and thus you increase the performance of IDS. And as you know, the performance of IDS is really important. What are the current keywords supported by TLS? We've got TLS version, which matches the TLS version of used in the uncheck. We've got the subject, which is doing a string match on the certificate subject, and we've got TLS issuer DN, which done a string match on the certificate issuer DN. We've got more to come. This is currently work in progress, and we will describe the evolution. I will describe the evolution later. What can we do with that? For example, let's have a classical settings with a company running some servers and having its own official PKI. If it has its own official PKI, every certificate on all servers have to be signed with this PKI. If we don't have that, we have something rogue that has been deployed on the network. This is or an administrator that has not put the correct certificate. We should have an alert on this. Or worse, which is a hacker who has put some service, some service that should be stopped. And to do so, it's really easy. We just do an alert with a TLS protocol. We do this for any flow in direction to all servers with $servers variable. And the match is done on if the issuer DN of the negotiated certificate is not the one we know. That's it. That means the certificate that is used for the TLS uncheck is not something that has been made by our own certificate authority. This is simple to write. You just have to know your certificate authority, and you've got some really security features that is provided by this system. There is other example that can be provided. This one is one of the main motivation behind doing the SSL on TLS support is to detect the mismatch between the certificate provided and the certificate authority who has made the certificate. For example, it is well known that google.com is signed by Google Internet Authority. It is not signed by DigiNota, sorry for the Dutch. And if we detect this, this is really, really bad. Thus, we can, in IPS mode, for example, make a signature which is drop, not alert. Drop will drop the packet. And if any of our clients connect to something that is in the subject google.com, but which is in fact not signed, see the exclamation mark before TLS is toward the end, which is not signed by Google Certificate Authority, then in this case, we drop the packet, we block the connection. That means you will be able to check that your certificates, that your client inside your network will not connect outside to a rogue server serving invalid google.com certificate, traditionally used for phishing or things like that. But I've heard, sorry for the Dutch again, that campaign has been hacked too, another certificate authority has been hacked, and thus for that we can, as we are doing some string matching, we can do it more violently and say, okay, if the URL is something coming from the Netherlands, I want to drop the packet. Okay, I don't recommend this in production, that could be bad. I think there is some certificate authority left. There is some current limitation on this TLS support. For example, we just do the match. We just are doing the match on the first certificate. We do not. We are not able to do the match on the whole certificate chain because you've got so you can have some certificate authority that is a sub-certificate authority, but this is already parsed by the backend. What is just missing is the keywords and the syntax for the signatures. Thus, you should have this very soon available. The same thing is true for some keywords that are still missing. For example, we can check the cryptographic algorithm which is used to do the TLS to use in TLS, and that can be really useful. For example, you've got the Tor attack by Eric Fiol, which has been discussed lately, and it was working by downgrading the protocol on some Windows OS by using a virus. And by doing this, we could check that the protocol are not being downgraded from what we expect as security level in the protocol used. And we can do the same with case size, which is related to the security and quality of the cryptography and the defilement parameters. And last point in SSL support is do some statistical study. For example, being able to have a hash of certificate that we will detect when it changes. For example, it will permit us not to depend on explicit rules like google.com is signed by google.com certificate authority. I give a speech back to Julien.
10 minutes? Okay. File extraction is what we're currently working on. In my opinion, a very exciting feature, although we have limited to HTTP currently, and we're working on SMTP as well. The idea is pretty simple. We track the HTTP sessions in a very detailed way, so if there is a file download or upload, we pretty much know exactly where it is in the stream. So why not extract it? We can extract it from GET requests, for example, but also from POST requests and PUT requests. Let me skip a little bit here. So what we can do is just pretty much drop the files into a directory, and we put in a little meta file which has some more information about it. I will show that later. But dropping it into a directory will enable you to have third-party tools like an antivirus, or you could check MD5 checksum, or you could check, you could send it to some SandNet or something and run the malware if it's an executable. So it will allow you to easily do more detection than you would with just looking at the network traffic itself. But we didn't stop there. We really only started because the interesting thing for me, at least, is where magic comes in. And magic is not real magic, of course, but it's we use lib magic to determine file types. And lib magic, you might all know it, or you might not know that you know. It's what powers the file command in Unix or Linux. It is the command that you can use to determine almost any file type and see what it is. To really get to the power of this, we needed to do rule extensions, rule language extensions, and that's what I'll discuss next. A little bit about Suricata rule language. It's a subset and superset of the Snort language. We left out all kinds of things nobody uses, no rule set actually uses, and we added some new things like the TLS work and like the file extraction things I will be talking about. Well, this is a very simple Snort rule. There has been a few in Eric's examples already, so I'll skip that part. So the rule extensions for file magic, for file extraction. The first one is file magic. And what it does, it sends the file, or the file is interpreted with libmagic, and libmagic will tell us in a string what the type of file is. And for example, it will tell us that a file is an executable for MS Windows. And you could create a rule like this that says, I want to see an alert if we see a Windows download. Then the next option is the file store command, file store keyword. And it will do nothing for detection. It will only say if the rule actually matches, store the file to disk, and we can inspect it further there outside of Suricata. The third rule keyword is the file X keyword. And it's very simple. It just matches on the extension that is claimed in the request. So you download a file or you upload a file, you give a file name there. It might not match the actual file type. And this is what you can see here in the rule. We match on a file that has a JPG extension, so we expect a JPEG file. But in the file magic, you see with the exclamation mark that the rule matches if it's not actually a JPG file. And this has very useful use cases, I think. Finally, we also added file name, which is just a simple file name match. So if you have some kind of naming scheme where everything that is secret has secrets in its name, then you could match on it here. So a real example. Say you have a web server and you only accept PDF uploads to it, and your user interface makes sure that normal users will not be sending in PDFs. So if you would see a file that's not a PDF that's being uploaded, someone is bypassing your user interface and trying something funny. Well, here you can see a more detailed rule on how we would prevent or alert on that. So we have a rule that is on HTTP. It comes in from the outside world to our web server. It is to the server, a post request in HTTP. It's to upload.php. And then if the file is not a PDF document, we alert and we store the file for further inspection. As an extra check, I also created the same rule, but then not on the file type, but on the file extension. So if the file extension is not PDF, then something is going on as well. Another example. I think you would want to know if your private keys are being uploaded or downloaded somewhere by accident. So this will match on an RSA private key. You could even leave out the RSA part, and it will match on any type of private key if you would have one. You could also, of course, store this file, and if it's not yours, you now have it, which can be used for interesting things, but that's for you to decide. So one final example here. My girlfriend, she's a photographer and an photography artist. And she has a Canon camera, and she uses the RAW format for optimal quality of the files. But she never wants to send those to anyone. She wants to print, she sends another file type, or if she has a modification of her files in Photoshop, she will never want to send anyone a Photoshop file, but a simpler file, because in photography, the number of prints that are publicly available really determines the price level of your photos. So it's really your secret source files, kind of. So this would be two rules that would drop any outgoing uploads for Canon RAW files or for Photoshop images. And I'm still trying to convince her to use GIMP, and for GIMP you would have a similar rule. So the file is stored to disk. It's just dumped in a simple directory with a meta file. The meta file looks pretty much like this. You have a timestamp, source IPs, etc., and the file name as it was claimed in the request, and the magic, which is in this case an executable for Windows, and the file size is also interesting. We have some limitations currently. It's a work in progress code. I meant to have it committed to the publicly available Git tree, but just failed to do that. So it should be out there probably next week. Limitations, obviously, protocols, only HTTP now and later SMTP. We have no plans for other protocols yet. Storage limits. Currently, I ran a large test, and I had 200,000 files on my disk, which is kind of too much, even if you wanted to delete them. And Microsoft is making things hard for us because most files have their magic on the start of the file, where you can determine what the file is. But Microsoft Office files, you can recognize them at the start of the file, but whether or not it's a Word or an Excel or whatever file is on the end of the file, which makes inspecting this very hard. Wrapping up, our development cycle is about 2 monthly. We just had a release last week. Our next one will be probably in January. The development priorities are determined on public brainstorm sessions where everyone can come and have their say. The last one was at RAID in September, and before that at RSA San Francisco. We have a public roadmap, bug tracker, etc., so you can see what we're working on. If you're interested, I advise you to use the source, but you can also use Debian, Ubuntu, Fedora, although the versions are slightly outdated. Or you can use a more specific security union or SmoothTech distribution. Thank you for your attention, and I'd be happy to answer any question.